Welcome back to the Deep Dive. Today we are opening up the hood of language technology to look at, well, a kind of hidden war.
That's a good way to put it.
It's a conflict that's been simmering for decades, right inside the software we use every day. You know, when you talk to your phone to set an alarm or when you type something into a search engine, you just assume it's one seamless, magical process.
But it's not. It's actually two very distinct forces at play.
And the funny thing is, for a long time, these two forces didn't really get along. I mean, they barely even spoke the same language.
It's a classic case of a house divided. It's a bit of a head versus heart situation, scientifically speaking. Or maybe more accurately, truth versus speed.
Truth versus speed, I like that. We're doing a deep dive into a really important paper by Junichi Tsuji called Bridging Computational Linguistics and Natural Language Processing.
It sounds technical.
Oh, it is. Let's be honest. It is. But the story here is basically a diplomatic mission. Tsuji is trying to broker a peace treaty between two groups that just drifted apart, the computational linguists and the natural language processors.
Which, to an outsider, that sounds like the exact same job title. I mean, if you told your grandmother you were a computational linguist or an NLP engineer, she's probably just going to assume you fix printers.
Right. I always assumed they were synonyms. If you work with computers and language, you're in that bucket. But according to Tsuji, they're more like distinct tribes with, very different religions.
That is a fair analogy.
And understanding that tribalism is key to figuring out how AI actually processes what we say.
It really is. And we should break down the tribes because their motivations, they explain the whole mess we got into.
Okay.
On one side, you have computational linguistics, or CL. These are the scientists focused on rational understanding. They're the architects. They care about grammar, formalisms, and the deep, almost philosophical why behind a sentence.
So they're the purists. They want the computer to appreciate the poetry of the syntax.
In a way, yeah. They want the representation of language to be, like, chemically pure. They build these massive, complex frameworks to describe exactly how English or Japanese or whatever works.
Okay, so that's one side.
Then on the other side, you have the NLP folks, natural language processing. These are the engineers. They don't necessarily care if the computer understands the deep soul of a sentence.
You just want it to work.
They just want the computer to process the text without crashing, and they want it done yesterday. They're the move fast and break things crew.
Exactly. So they value efficiency, robustness, speed.
Precisely. And for a long time, these two groups drifted apart. The engineers found that statistical tricks, just counting how often words appear next to each other, could get results fast without needing all that heavy academic linguistic theory.
But Tsuji's argument, and the mission of this deep dive, is that we've kind of hit a wall with that approach.
We have.
A wall. I mean, it feels like language AI is getting better every single day.
It is, but there's a ceiling to how far dumb statistics can take you. To get to the next level of AI, to things like true text entailment, where the computer actually understands implications.
Like realizing the cat ate the mouse implies the mouse is dead.
Exactly. You can't just count words to get that. You need structure. We need to bring the soul of linguistics back into the body of engineering.
So let's unpack this great divide. Why did they split up in the first place? It seems so logical that if you want a computer to speak English, you should ask a linguist how English works. Why did the engineers stop listening?
Well, the core friction comes down to two words: declarative versus procedural. This is the fundamental disconnect that Tsuji highlights.
Okay, lay it on me. What's the difference?
Computational linguistics focuses on declarative representation. That means they define what the roles are. They create a grammar that says, this noun connects to this verb in this specific way to create meaning. It's a static map of truth.
Okay, so it's the rule book. It lists every single legal move in the game.
Yes, but NLP focuses on procedural processing. They ask, how do we compute this efficiently? Just because you have a rule book doesn't mean you have an efficient way to read it during a game.
I see. So the linguist hands over a grammar that's perfectly accurate, describes every nuance of the language, but maybe it takes the computer 10 minutes to analyze one sentence because the rules are so complex.
Exactly. And historically, there was this massive misconception, largely dating back to Noam Chomsky and his standard theory in the 60s. This is a really important context.
Okay.
People fell into the trap of thinking that a grammar theory was a literal description of how the human mind, or a computer, processes language step by step.
Wait, explain that. If Chomsky writes a rule saying sentence equals noun phrase plus verb phrase, isn't that how our brains do it? Isn't that the code running in our heads?
Not necessarily. That's the psychological reality fallacy. Suji points out that we confuse the map with the journey.
A map versus a journey.
Think of it like a map of a city versus driving instructions. A map shows you where everything is relative to everything else. That's the declarative grammar. It shows the truth of the layout. The library is north of the bank. That is true.
Okay, I'm with you.
But it doesn't tell you the most efficient route to drive from the library to the bank at rush hour. That's the procedural processing.
And we just assumed they were the same thing.
We thought if the map was complex, the driving instructions had to be complex and slow. Because the linguistics were heavy, we assumed the software had to be slow, so the engineers just threw away the map and, started driving across lawns to get there faster.
But Suji says that's not true. We can have a complex map, but find a fast route.
He proves it, and he does it with a really fascinating experiment involving two heavy hitters of the grammar world, LTAG and HPSG.
This is the tale of two grammars. This part of the paper blew my mind a little bit because it just challenges that idea that data is data. It turns out the shape of the data matters just as much as the content.
It matters immensely.
So introduce the contenders.
In the red corner, we have LTAG lexicalized tree adjoining grammar, and in the blue corner, HPSG head-driven phrase structure grammar.
Those are absolute mouthfuls. Without getting bogged down in the acronyms, what's the visual difference? If I could see these grammars, what do they look like?
Imagine LTAG is being built out of Lego blocks, but not single bricks pre-assembled chunks.
Okay.
You have a chunk for the cat, a chunk for eats, and a chunk for the mouse. These chunks are called elementary trees. It captures things like idioms and multi-word expressions really well because it treats them as whole units.
Okay, so LTAG is big, chunky puzzle pieces. You're snapping together pre-made sections.
Right. Now, HPSG is different. It's more like a set of strict constraints or principles. It's less about pre-made chunks and more about rules for binary branches, splitting things into twos.
Okay.
It describes language as a series of features that all have to match up.
So the experiment. Suji and his team do something sort of magical here. They took an LTAG grammar, this big, chunky, complex system, and they mathematically converted it into an HPSG-style grammar.
And here is the crucial detail. They managed to make them strongly equivalent.
And what does that mean exactly? Strongly equivalent.
It means, for any given sentence, both grammars produce the exact same linguistic interpretation. The meaning is identical. The relationships between the words are identical.
So it's the same information, just formatted differently, like saving a Word doc as a PDF.
In a sense, yes. The content is preserved perfectly. The linguistic truth remains the same.
But then they ran parsers programs that analyze sentences using these two formats. Now, if the information is the same and the result is the same, you'd expect the speed to be roughly the same.
Right? One would assume so. But the results were, well, they were shocking. The parser running the HPSG-style grammar was 13 times faster than the original LTAG parser.
13 times. That's not a rounding error. That's a different species of speed.
No, we are talking about 1.54 seconds to parse a sentence versus 20.76 seconds. In the world of real-time computing, 20 seconds is an eternity.
It's a difference between a conversation and sending a letter. Why? If they mean the same thing, why was one so much faster?
It comes down to the shape of the data and how algorithms handle it. Remember, LTAG uses those specific elementary trees.
The puzzle pieces.
The puzzle pieces, exactly. And when the computer tries to parse with them, it has to merge these complex trees. This leads to what we call a combinatorial explosion.
That sounds dangerous.
It's dangerous for your processor. Because the pieces are so complex, there are just too many ways to combine them. The computer has to check massive amounts of possibilities to see which pieces fit. Does this chunk go here? No. Does it go there? Maybe.
Okay, so the LTAG chunks are like oddly shaped puzzle pieces that are hard to fit together quickly. You have to twist them and turn them a lot.
Whereas the HPSG version sliced those trees into binary branches, just two paths at every single junction. This allowed the computer to use a standard, very efficient algorithm called CKY.
CKY.
It stands for Cock Younger Kasami. It uses dynamic programming. Think of it like the game 20 Questions. If you ask a question that splits the world in half, is it a living thing? You eliminate half the possibilities instantly. Binary branching lets the computer make a series of rapid yes-no choices.
So because HPSG was formatted as a series of binary choices, the computer could just race through it.
Exactly. It's so much easier for a computer to make 1,000 simple yes-no choices than to try and fit 5 complex irregular shapes together.
So the key takeaway here is You can keep the complex linguistic truth, the soul,
Right, the soul.
but you can change the shape of its body to make it run faster. You don't have to dumb down the linguistics to get speed, you just have to reorganize it.
You decouple the representation from the processing. That is the first pillar of the peace treaty. You keep the CL truth, but you use NLP engineering to execute it.
Okay, so that's the first victory for reintegration. But the paper brings up another huge bottleneck in deep linguistics, something called unification.
Ah, yes. Unification. This is the heavy lifting. If parsing is the journey, unification is carrying all the luggage.
It sounds like a cult ritual, but in this context, it's a math problem, right?
It is. In these deep grammars like HPSG, words aren't just simple labels like noun or verb. They are complex bundles of features.
What do you mean?
Well, cat isn't just a noun. It's a noun. It's third person. It's singular. It's animate. It expects a verb that can handle a singular subject.
So every single word is carrying a heavy backpack of data.
Exactly. And unification is the process of checking if the contents of two backpacks match. If I want to combine the cat with eat, I have to open both backpacks and compare every single feature.
A simple check says noun plus verb is good.
But a unification check sees that cat is singular and eat is plural, so they don't unify. The backpack contents clash. It fails.
And doing this for every possible word combination in a long sentence must be.
Computationally incredibly expensive. It is so slow. This is why the engineers usually ran away from HPSG. They said, we can't check backpacks for every word. We'll be here all day.
So Tsuji proposes a solution called CFG filtering. And I love the logic here because it feels like a hack, but a really smart one.
It is brilliant engineering. It's all about creating a cheap filter.
How does it work?
Imagine you are security at a massive stadium. If you do a full background check, fingerprint scan, and interview on every single person trying to enter, the line never moves.
Right. That's full unification.
That's full unification. You'd never get anyone in their seats before the game ends.
Okay.
CFG filtering is like having a ticket checker at the outer gate. They don't check your ID, they don't check your pockets, they just glance and say, do you have a ticket? Yes, go. It's a rough check, it's fast.
So in the computer, how do they build this ticket checker?
They derived a simple context-free grammar, ACFG, from the complex HPSG. They basically stripped out all the detailed info in the backpacks and just looked at the labels. This simple grammar is a rough draft.
But wouldn't that let mistakes through? I mean, if I say the cat eat fish, the labels noun, verb, noun look fine, even if the grammar is wrong.
Yes. It overgenerates. It might let a sentence like, the cat eat fish pass through the first gate.
But that's okay.
It's okay because it is lightning fast. It throws out 90% of the impossible options, the stuff that is verb, noun, adjective, or just total gibberish.
So the process becomes run the fast, dumb parser first, clean out all the junk,
Right.
and then you only do the expensive unification background check on the few options that actually made it through the gate.
Exactly. They found that global filtering, checking the whole structure simply, is much more effective than doing quick local checks. By the time you get to the heavy lifting, you've eliminated almost all the wrong paths.
This feels like such a practical life lesson, too. Don't sweat the details until you know the basic structure works.
It is efficient engineering underpinning scientific understanding. The paper notes that by using the CFG backbone, they avoid the cost of unification for all the partial parses that are destined to fail anyway.
Why check the backpack if the guy doesn't even have a ticket?
Exactly.
Okay, so we have better data shapes, these binary trees, and we have a security checkpoint, the CFG filtering, to filter out the junk. But we still have the issue of ambiguity. Real language is messy.
It is. The classic example. I saw the man with the telescope.
Did I use the telescope to see him, or did the man have the telescope?
Syntactically, both are valid. The grammar allows both. But one is usually more likely given the context. This is where we need probabilistic models.
The computer has to search for the most plausible meaning.
Right, on all the valid ones. And this leads us to the third case study in the paper, super tagging.
This sounds like a superpower. Look, up in the sky, it's Super Tagger.
It's a superpower for parsing, certainly. Tsuji's team compared 3 models to find the best way to handle this ambiguity. They wanted the best figure of merit, essentially a score to help the computer guess which path to take.
Walk us through the contenders here.
So Model 1 was a standard bottom-up approach, similar to a probabilistic CFG. It calculates probabilities from the words up. But the problem is, it makes errors early on. It's looking at the leaves of the tree without seeing the forest.
It's flying blind.
A bit, yeah. Model 2 used super tagging. This looks at the local context of a word. its neighbors, to guess its detailed grammatical tag before even trying to build a tree.
So if I see the word the, I know the next word is almost certainly a noun or an adjective.
Right. It's definitely not a verb. But HPSG tags are really detailed. Super tagging tries to assign these complex descriptions based on local evidence. It's like guessing someone's job just by looking at their shoes. It's a heuristic.
Then Model 3.
Model 3 combined them. But the real breakthrough wasn't just the model. It was the staged architecture that Suji proposed. It is a pipeline of efficiency that puts everything we've discussed into a sequence.
I have the steps here in the diagram from the source. It's like an assembly line. Step 1 is POS tagging.
Part of speech tagging, just basic labeling, noun, verb, etc. Very fast.
Step 2, super tagging.
Using that local context to guess the complex, heavy tags we talked about, narrowing down the possibilities.
Step 3, CFG filtering.
That's our security checkpoint, checking if the tags form a valid structure globally. It takes the guesses from the super tagger and makes sure they build a coherent skeleton.
And finally, step 4, the deterministic parser.
The final, deep check. This creates the full, deep linguistic structure with all the unification.
Now, the numbers here are what really sell this argument. I want to make sure I got this right. Using Model 1 the old way, the average time to parse a sentence was 674 milliseconds.
Roughly 2/3 of a second, yeah.
With the stage architecture doing more steps, effectively it dropped to 29.6 milliseconds.
That is a roughly 95% reduction in time. It's counterintuitive, isn't it? Doing 4 distinct steps results in less time than doing one big step.
It works because each step is a filter. The POS tagger is cheap, the super tagger is a bit more expensive, but it narrows the options significantly. The CFG filter is a broad net. By the time you get to the expensive parser, there is almost nothing left to confuse it. You're only doing the hard work on the winners.
Exactly. It turned a heavy academic crawler into a sprinter.
And crucially, without losing accuracy.
In fact, accuracy improved because the super tagger made better local decisions, avoiding those garden path errors where the computer gets confused by the start of a sentence.
So bringing this all together, the paper started with a feud. The linguists wanted truth, the engineers wanted speed. They ignored each other for years. What's the verdict?
The verdict is that we don't have to choose. Suji references David Moore, a famous neuroscientist, and Moore distinguished between the computational level, what needs to be done, the theory, and the algorithmic level, how to actually do it.
So the breakdown was that we tried to jam the theory directly into the algorithm.
Exactly. We thought the grammar was the algorithm. We thought if the theory is heavy, the code must be heavy. Suji shows that you can have a high-level, complex declarative theory and then translate that into a completely different optimized architecture for the machine to execute.
It's a reintegration. It's bringing the architect and the builder back into the same room.
And admitting they were both right. The linguists were right that you need deep structure to understand meaning. You can't just count words if you want AI to really understand entailment or logic.
But the engineers were right that you need efficient filtering and approximation to make it work in the real world.
It's really a blueprint for collaboration. Efficiency doesn't come from discarding complexity. It comes from organizing it intelligently.
Using simple filters to manage complex truths.
That is the core lesson. And frankly, it's a lesson that applies to almost any complex system, not just linguistics.
So before we sign off, I have a thought that's been nagging me while reading this. It's a bit existential.
Go on.
We saw that they can convert one grammar into another L tag to HPSG and get the exact same meaning, but totally different processing speeds. It makes me wonder, does grammar actually exist in our brains? Or is the grammar we study just a code we wrote to describe something we don't understand?
That is the ultimate question.
I mean, if the computer doesn't care which grammar it uses, as long as the math works, maybe our brains are doing something totally different, and nouns and verbs are just the user interface. Maybe the truth the linguists are chasing is just one possible map of many.
If the map can be redrawn a dozen ways and still get you to the destination, is the map real? Or is only the destination real? Suji proves we can change the map without losing the destination. Whether the brain uses trees or dependencies or just massive statistical vectors, that is still a mystery.
Something to mull over next time you're diagramming a sentence. Thanks for listening to this deep dive into the hidden mechanics of language.
It's been a pleasure.
See you next time.